So in this lecture we will see the disadvantage of Nyquist first criteria and how Nyquist second criteria overcome that disadvantage. As we have seen in the previous lecture that Nyquist first criteria has disadvantage that my pulse bandwidth, which was initially minimum required in the ideal solution, is increased from RB by 2 to RB. So this is a disadvantage, that is my bandwidth has increased. So how to overcome this disadvantage? The solution is given by Nyquist second criteria. We will see. Now question is how to revert back that increase in bandwidth. The increase in bandwidth can be reverted by expanding the pulse in the time domain. As we know the rule that if the time expansion in time domain causes compression in frequency domain, or expansion in frequency domain causes compression in time domain. Now in this case what I do is, if I expand time domain, so time domain if expanded, then it will cause frequency domain to compress. That is, this is what is the working principle of Nyquist second criteria. So in this case what we have done is, we have chosen a pulse P and TB which is 1 for n is equal to 0 and n is equal to 1. That is, for 0 and 1 it will remain for TB equals to, actually this is for n is equal to 0 means P0 TB, that is P0, and n is equal to 1 means PTB. So for 0, for two time instant, one is for 0 and other is for TB, my pulse will remain 1. So at these two instants it will remain 1, then after it will come down. So in other word I am expanding the pulse in time domain. This will cause the compression of the pulse in frequency domain, and this is my objective, and this is the working principle of Nyquist second criteria. This can be seen from this particular example. As this can be seen here, there are two pulses. This is corresponding to two bits, bit 1 and bit 2. This is Nyquist second criteria pulse, that is for t is equal to 0 and TB. Actually this point will come here, not here. Okay, this is not drawn correctly. So this point will come at TB. So for one, this is the first pulse. For another one, this is the second pulse. So in that case, what is happening is, you may ask this that again there is an interference. Yes, there is an interference between two pulses, and this interference has been introduced intentionally to reduce the bandwidth. So you may ask this, then when there is an interference especially at sampling instant TB, you can see this is an interference, and at this point 1 plus 1, it has become 2 volt. My sample value has 2 volt because my sampling instant will remain same, that is TB, 2 TB. So at these sampling instants again I am suffering from interference. So this, you may ask the question, why then, how this interference will not affect the proper detection at the receiver? So your concern is right. Now we will see that this intentionally introduced interference, which is called as a controlled interference, or this is also called as a partial response signaling, this can be easily detected by using an appropriate decision rule at the receiver. We will see this now. So let us consider, to explain this further, let us consider a sequence information bit, that is IK 1 0 1 1 0 0 1, which is to be transmitted. And then what I do is I do polar signaling, that is 1 is represented by 1 volt. This is an information bit and this is a signal in the voltage or voltage level. This is 1 minus 1 because it is a polar. This 1 is represented by 1 volt, this one is represented by 1 volt, and so on. Then after, if we transmit this particular case using Nyquist second criteria pulse, then what is going to happen is we have to think this, we have to keep this diagram in mind, and especially at sampling instant. This is my sampling instant, this is my sampling instant. So in that case, what is going to happen? What would be the values of sampling instant is an important question. So at t equals to 0 corresponding to 1, I'll get 1 volt. Now at t is equal to tb, I will get the interference. These two pulses will interfere, these two voltages will interfere, and whatever I get at the sampling instant is sum of these two voltages. So 1 volt plus this 1 volt plus this minus 1 volt will yield 0 volt. In the similar way, this will, so it will occur at this sampling instant. At this sampling instant, value is 1. At this sampling instant, the value will be, at this sampling instant, the value will be sum of this plus this. Similarly, at next sampling instant, my third sampling instant, my value will be sum of these two because of interference, because I am using Nyquist second criteria pulse. So the sum of these two is 0. Then after my next sampling instant, what I get is the interference of two adjacent pulses. 1 volt plus 1 volt will give me 2 volt. Similarly, at the next pulse, at the next sampling instant, my next sampling instant is this. I'll get sum of these two, which will give 0 volt. At the next sampling instant, I'll get the sum of these two, which is minus 2 volt. And at the next sampling instant, I'll get the sum of these two, that is 0 volt. So at these sampling instants, what I'm going to get is 1 volt, 0 volt, 0 volt, 2, 0, minus 2 and 0, all values in volt. My question is, if I am able to get back actual information bits from these sample values, then I can justify, I can validate that even if there is this interference, controlled interference, intentionally introduced interference between two pulses, but this scheme is going to work. In other words, this interference has no effect in the detection, and we will have the advantage of interference is that we have reduced bandwidth from RB by 2, from RB to less than RB, some value which is less than RB. So now how to get this particular information from this particular sample values? That will be, for that we have to decide a particular rule which is called as a decision rule. So now we have to see what is a decision rule. What can be the decision rule? So that we get sequence 1 from sample values 2, and this is what is shown here. If we choose this decision rule, that is YKTB is a sample value, that is KTB is sample value. If it is greater than 0, you decide in favor of bit 1. If this value is less than 0, you decide in favor of bit 0. And if YKTB is exactly 0, then you flip whatever was there in the previous bit. The spelling is not correct. This is flip or revert. So in other words, if my sample value is 0, then according to decision rule, I have to see just previous bit, and my current bit would be just reverse of the previous bit. So let us apply this decision rule into this sample values. First, this is a 1 volt, so the bit is 1. This is a 0 volt, so which means this case 3. So I have to revert, my detected bit will be revert of the previous bit. My previous bit was 1, so my current bit will be 0. My next sample value is 0, so case 3, that is my current detected bit will be reverse of the previous bit, that is from 0 it will become 1. Now my current sample value is 2, which means I am in case 1, so my detected bit is 1. Now my current sample value is 0, which means case 3, so my current detected bit will be just reverse of the previous bit. Previous bit was 1, so now my current detected bit will be 0. Then I have minus 2, sample value minus 2, that is case 2. In that case I'll get 0 volt, and then I have my current sample value 0 volt, which means a case 3, which means my current detected bit would be just reverse of the previous detected bit. So what I got from this decision rule is this. What I got from this decision rule is this, and this is exactly same as this. What is this? This is at the receiver. What is this? This is at the transmitter. So what I detected at the receiver is exactly same as at the transmitter, which means that the amount of interference, the type of interference that I have introduced has no effect in the detection. So, however, but it has advantage that by intentionally introducing that interference, I have advantage that my bandwidth, which was from minus RB to plus RB in the Nyquist first criteria will come down, maybe from minus RB by 2 to plus RB by 2. And this particular signaling is called as controlled ISI, as expected, because intentionally we are introducing interference, that too in the control way. This is also called as partial response signaling, and this is also called as Nyquist second criteria of 0 ISI. And this particular pulse, which is defined by this equation is called as Nyquist second criteria pulse. In the previous lecture, the pulse that we had seen was Nyquist first criteria pulse, that with 0 ISI. This is a Nyquist second criteria pulse. Now you may ask one question as to how to generate that Nyquist second criteria pulse. This is shown in this diagram. As you can see that we have information bit, we are passing it through polar signaling. Then after a delay of TB bits, this output AK and its previous sample value AK minus 1, which is obtained from this 1 bit delay, they are added together. So this particular section will induce that partial or controlled ISI effect, and then after I am using Nyquist first criteria pulse, and the effect of whole this will be Nyquist second criteria pulse. So this particular diagram is basically a generation of Nyquist second criteria pulse. Wow, there is one example of Nyquist second criteria pulse. This is an example of Nyquist second criteria pulse, and this pulse is in time domain and its frequency domain or Fourier transform is this. As you can see, this is a rect function. This is a rect function of duration RB. So, and what is this? Is a cos. So which means it will look like this. So the total width is your RB, that is from minus RB by 2 to plus RB by 2, and this is in frequency domain with the maximum value, that is 2 by RB. 2 by RB. So what is this? This is your Nyquist, one of the example of Nyquist second criteria pulse, and the whole process is your Nyquist second criteria for 0 ISI. It is important to mention here that this can easily be generated with the help of MATLAB, and this also can be verified with the help of MATLAB, that once we take the Fourier transform of the pulse, that is PT, that is this pulse, we can take the Fourier transform, we'll get this also. Theoretically and practically this can be proved easily. And another important point is there is some disadvantage of Nyquist second criteria pulse, and disadvantage is that corresponding to bit 0, suppose this is a bit 0, now my sample value is 0. In this case, my detection of the current bit is based on the nature of the previous bit. Now suppose during transmission this previous bit get erroneous, that is rather than 1 it is received as 0. In that case my current decision would be 1 rather than 0. In other words, these detection of the sample value 0 depends on the nature of the previous bit. If my previous bit is erroneous, then my current detection will be erroneous. This is a disadvantage of Nyquist second criteria. How to remove this disadvantage we will see in the next lecture.